Homework 2 is going to be for tonight from the book. And we do just kind of move forward with the assumption that you're like really good at the chain rule, even though that may still need a little bit of practice. Don't worry, we have some days in here on the schedule planned for some practice days. We have don't worry. So we will have plenty of time to become good at this, I think. Let's I don't know. Let's do this real quickly, just because it's a nice process. This is before our lesson today. Kind of. This is not the bulk of what we're going to do today, but I think it's worth doing. So I forgot I had this on here. All right. So would you just try this example with me real quick, and we'll give it a try here. And here we have this is weird that we're asking for dy dt. I promise, Knut and others. There are no typos on this slide, and I really do mean dy dt here. And dx dt. There's a lot of symbols to figure out what they mean. At first, it seems like a really great property. Like, oh, quadratic. I could take the derivative of that. If you're at first intimidated by what this is even asking, don't look at what it's asking. Just do what you think you know. No, I just mean, what would you like to do? Forget what the problem says. What did you think that this was going to ask here? It's calculus class. What were you going to find? What would you like to have been asked? dy dx. So feel free to find dy dx. You know how to find that one. X is 1, don't you? So do it, just for fun. Just for fun. Figure out what dy dx is. And that's not what we seek, but maybe it's interesting. And then maybe you do something. Yeah. I don't know. We keep going then. What's dy dx at x equals 1? What do you get? All right, so but we still want dy dt. So Jack, help us out here. So talk to us. Don't just give us an answer, though.
Okay. So dy over dx does not equal dy over dt over dy or over dx over dt. Then it's just that over 1/3.
Yeah, and this is all when x is 1 here.
And wait, and that equals 9. So
And this is 9. dy dt is the thing we don't know.
Yeah.
And dx dt is 1/3. I think that works. Oh, I'm sorry, 3. 9 times 1/3. Yeah. All right. So I just thought it'd be worth showing you one like this. I mean, you've got a parabola that, we can still have on this parabola some particle that's moving and track its velocities left and right or something like that. It's and up and down. Yeah, Amy.
I still don't understand how you got to the top right.
Yeah, so this is like a thing that we learned on Friday, which is just like a kind of a recapitulation of the chain rule. This fact, is this the fact that's disturbing you? Which we used in the warm-up today too, just a second ago. Right? We stack them. Yeah, Rosie.
Like, the dx dt equals 1/3 when t equals 1 and not when x equals 2. Like,
Oh, that's a t equals 1, huh?
right. So is that
Let's think if that's a typo, whether we could actually do it that way.
right, like
Could we figure out when t is 1, what x is? I don't know. Or when x is 1, what t is?
So you just plug in, instead of making it 9, like make y dx, just keep it to the 7 and then get the function.
And then get the function.
So you do 2x plus 7 equals dy dt over 1/3. Is that allowed? Is that
2x plus 7 equals dy dt over 1/3.
yeah. And then just have the like
Oh, I see what you're saying. So 2x plus 7
yeah.
equals times a third. But then what's t, though? When t is 1, that's what Rosie's asking. Yeah, I think it has to be a typo. I'm trying to think if there's any way to recover that otherwise. Yeah. When x is 1, I guess. Yeah. All right. So we've been taking derivatives by, if you were to look at this function here, x squared plus y squared equals 1. We've been up until now, or if I gave this to you now, you would probably want to solve for y and take derivatives. But it'd be worth considering, especially in cases where you can't possibly solve for y, how to interpret taking the derivative of this equation just like straight out. And so we're going to show you how that can be done today. This is called implicit differentiation. So I can take the derivative of everything in this equation on both sides. I'm just taking the derivative, choosing to take the derivative of whatever I want to take the derivative with respect to. In this case, we're usually we like to think of x as being the independent variable. So we'll be taking all the derivatives here with respect to x. And most of these are things you know and love, like dx of x squared. What's the derivative of x squared with respect to x? 2x. What's the derivative of 1 with respect to x? 0. The only one that's a little weird is this one right here, dx of y squared. So what is the derivative of y squared with respect to x? That's a little weird. Our first guess might be just 2y. But of course that's the derivative of y squared with respect to y, right? Yeah. Well, we don't know what y stands for yet, but it's some function that involves x. It depends on x. If it didn't depend on x at all, then that would be one thing. But y does depend on x. Yeah, actually. 1 minus x squared. Oh, you mean like y squared is 1 minus x squared. I think what you'll get then is kind of tautological. You'll get something that you get like 0 equals 0 on both sides if you do that. But I mean, you're right that y squared does equal 1 minus x squared. We need to keep in mind that y is really like y of x. It's like, you know, if you had some function of x here, and it's being squared. Well, what do we do in this situation where we have some function of our independent variable raised to a power? Well, we do 2y, 2 times whatever that thing is that depends on x is. But then afterward, we have to multiply by the derivative of that thing. So the 2x and the 0 are exactly what you said, right? Those are not a surprise to you. But what might be a little bit of a new idea to you will be the fact that when we take the derivative of y squared, we need to say it's 2y times, since we didn't take the derivative with respect to y though, we need to use the chain rule here. Multiply by the derivative of y with respect to x. It's exactly like as if someone was asking you to take the derivative of like sine y squared, right? With respect to, sine x. With respect to x, right? You'd be like, well, it's 2 sine x times the derivative of that, which is cosine x, right? So it's the same thing. We're just saying that, like, we've got some function so 2y, y prime, right? It's like we've got y as being something that depends on x, right? So just like we did here, what's the derivative of 2x squared? Sine x squared? It's 2 sine x. Oh wait, times cosine x. In the exact same manner, if we're taking the derivative of y squared with respect to x, then we need to have the exact same amount of caution, right? Yeah.
So, is it just a coincidence, or could it be like simplified that dy dx is equal to d dx times y?
It's not d dx times y, it's d dx of y.
Okay.
You mean like, are you asking, like, can you write it this way instead of this way?
I can't see. Yes.
And the answer is yes, you can write those, but just don't mistake this as being d dx times y.
Okay.
All right, well then we're not quite done in the place where we'd like to be. dy dx you might want isolated, so that's a thing we can do. And we get, in terms of x and y, just negative x over y. We can try that for a couple values on the curve, right? This is a circle, so there are a couple points you know, it's the unit circle. So like the point, if you plug in the point here, what are the x and y coordinates of that we would plug in here? X would be 1 over 0. What do we get there? Oh yeah, it's a vertical line, the tangent line there. So the slope there is undefined. You could try this point too here. What do we get there? 0, of course. What about this point right here? What are the coordinates at 45 degrees? Well, the slope we already maybe know. What are the coordinates of that point? No. Wait, what? Yeah, root 2 over 2 comma root 2 over 2, right? So plug those in, do you get negative 1? Yes, right? And that's the slope you would expect to get there. So this does seem like it's working. Yes, Jeff?
Wait, so like, are there two derivatives? Because it has like 2 points, or like, cause it's not a function, so it has.
At any given point, yeah, in order to use this, you need to specify both the x and y coordinate of your location on the circle. But that pins it down though, doesn't it? So there's no ambiguity in the questions I've just been asking. Like, what's the derivative at this point here? That point is root 2 over 2 comma root 2 over 2. So the derivative is, plug them in and you'll get the derivative there.
But then could we have, like, if you graph it, could you graph that derivative?
Could you graph that derivative? Not easily in its current form, no. So there are ways to do it. Maybe you can think of a way to do it right now. No? We will before too long. Yeah, you're gonna graph the derivative in like a plane rather than, it's gonna be like a function in the plane. We will be graphing, we will be thinking visually about these, and later we'll be doing something called slope fields, and you'll be looking at, slope fields is the answer to the question you're asking, but it doesn't come right now. We'll talk about it later. Notice here, both here and here, we get slopes of -1, and the equation kind of tells you that too. Let's try another one. Notice on this one that it's not even an option. On the last one, you might have at least been able to isolate y and be like, hey, y is equal to the square root of 1 minus x squared or something like that. And you could have had success there. But here, you can't even attempt solving for y. So the only means we have at all here of success will be actually doing implicit differentiation. So again, take everything with respect to x, the derivative with respect to x. X squared is not that interesting. We've done that, we've been there, we've taken a derivative of that before with respect to x. What's the derivative of 2y with respect to x? It doesn't have to be a product rule necessarily. I mean, it's just like if you were taking a derivative of like 2 sine x, what would you do? It'd just be 2 cosine x, right? So what do we get here? It's not sine x. It'd just be 2 y prime, right? 2 times dy dx. This one's a little messy. What's required here? Sine of y. That's going to be another chain rule one because we got y all up in a function, right? So it'll be cosine y. Oh wait, times y prime, right? So make sure you understand each one of these. Again, the 2x, that makes complete sense to you. Over here, notice the use, the absence of the use of the chain rule. Right? We don't need it there. It's just, it's not a function with y stuck into it. Whereas on the end, we have sine of y. Keep in mind that this cosine y is being multiplied by dy dx. Okay, that's not clear. All right, and then can we solve that for dy dx? Sure. Use some algebra. Collect like terms on the left side. Move everything that has a dy dx over there. Factor out a dy dx. In fact, I think there were 2 problems on the summer packet that we made you do where we had like an equation that involved x, y's, and z's, and we said solve for z or whatever. And some of them required that this type of algebra, and the reason we put that on the summer packet is just to make sure you're comfortable doing this kind of symbolic manipulation. Factor out the dy dx, divide by the thing that isn't dy dx, and you have your equation. By the way, this, who knows what this even looks like? This curve is crazy. What is it? Right? Is that a circle? No. Is that something else that we know and love? I don't know what it is. I'll graph it here if we go to the finish. And again, if I haven't said it already, and the title tells you too, this is called implicit differentiation because the curve we're working with is an implicitly defined curve, right? It's a term maybe you've heard before. Well, now in the context of calculus, we call this implicit differentiation. So, notice the thing we've been doing, a little 2-step process. And he said it on Friday, but the chain rule will always be with you from here on out in this unit. So notice how often the chain rule is at play. This is why we couldn't talk about really implicit differentiation until now. We have to kind of wait for you to understand the chain rule to even have this kind of conversation. Any thoughts? Questions so far? Let's make these things go very clear. Sorry, this is the question. This is like the first part of the answer up here, I guess. Sorry. Well, so we have some curve, x squared minus xy plus y squared equals 7. Sorry, graphed on the other line. And I'd like you to find, we'd like to find the equations of the tangent and normal lines to this graph at that specified point, which I guess is on the curve. We can just double check that if we wanted. Yeah, okay, it is on the curve. All right, I just wanted to make sure. I told you -1, 2 is a point that we're going to find equations of tangent and normal lines to this curve. But to make sure that -1, 2 is actually on the curve. But it's easy to check that. So start by finding dy dx. Of course, that's the thing we need to do. And then we have the point, so then we'll be all set. How do we, again, we have to differentiate x squared with respect to x. That's easy. Differentiating 7 with respect to x. That's easy. But what about the x, y, and the y squared? Y squared, that's not bad. I think we already did that today too. The derivative of y squared is 2y times dy dx. That we got. What about this xy in the middle? How do we deal with that? We haven't seen that today. What do you think, Ashley? She said it. Can you verify that we did it right there in the box in the brackets? I think everything else except the brackets is old news from the previous slides. But inside the brackets, it might be a little unsettling. Are you comfortable that that's in fact what we did? All right, cool. Okay. First, times the derivative of the second plus second times the derivative of the first. Oh yeah, I do see that. Okay. Well, no, that was the kind of the critical move. Everything else is clean up here. Algebra the rest of the way home. Distribute the negative. Isolate the dy dx. And then, we're not done yet. In fact, I don't know if it deserves a box around it yet. I don't know if that's something it deserves. I don't know. Because we're not done. What are we supposed to do? We're actually finding the equation of the tangent line, a normal line, to this point. So we need the slope at this point. Theoretically, that's what this does for us. Yeah, just plug in -1 for x and 2 for y into this. And what do you get? Was that 4 over 5? All right, now I think we're in the clear. We have the slope of the tangent line, at least, and we have the point, so the rest is us just writing the equations. Right? You don't have to do that, remember. The answers in the first set of boxes are just fine. Yeah.
Wait, so how'd you get m again? Because I was.
We plugged in negative into the, you're okay with the way we got dy dx?
Yes.
Okay, that was like the big crux of this problem. Then if you want the slope at a particular point, plug in for x -1 and y for 2. I'll go back and show you. Down here. Okay, so actually plug in -1 for x and 2 for y everywhere you see an x and a y. And you'll generate the slope. Yeah. All right, like I said, the first set of boxes is all that's needed. Only the second set of boxes, if asked, and I'll just tell you right now, no one ever will ask. Okay. I don't think anyone would ever ask. But some of you you just have like a personal affinity for slope-intercept forms. There it is if you want it. These are great up here. Okay, we do have one more thorny issue to take care of before we leave today. I want to make sure we get to one of these. Oh, it's so sad that this is here. Okay. All right, so the question here is now find d squared y dx squared. That is, find the second derivative here. So we'll proceed as normal. Nothing to say, nothing to see here. Everything's fine. Do you agree that that's the derivative?
Yeah.
Implicit differentiation here? Yeah? We'll solve for y prime. Everything is going great. Not much to say here so far, right? We haven't gotten to the second derivative yet. But do you agree that that's just us doing a problem very similar to the last couple slides? I'll give you a second to digest that. I just don't really have any commentary about that. Implicitly differentiate and then solve for y prime. So far so good? Well, guess what we're going to do again? We're going to take the derivative again, of course. We want a y prime. That will be, right away, the thing we want on the left side will be there, right? Y double prime. Yay. But on the right side, what are we going to have to do for this particular problem? We're going to need to do what? The quotient rule, which is not a huge deal, right? So do you agree that this is us doing the quotient rule on this? Bottom, y, times the derivative of the top, 2x, minus top, x squared, times the derivative of the bottom, notice, is y prime, right? All over the bottom squared. All right, so we're doing pretty well, but the only thing that's a little bit disconcerting here is that y double prime, our currently formula for y double prime, involves y prime. That's a little bit of a problem, and unfortunately this has been up here on the slide though this whole time. But that's okay, because we have a formula for y prime already, and you always will if you're doing this method. So we can substitute in, and we should always be able to get y double prime in terms of just x's and y's. Right? You should never have a formula for y double prime and leave it here with a y prime in it still. Okay? So that's okay. We can make this substitution. And now we have the answer. You can clean it up a little bit, obviously. You could even do other things to that if you wanted to combine fractions, but whatever. leave that up there and let people ask questions for a second if they have them. Is that clear? What's required for you? Study it. Yeah, you should.
Do you want to have notation that's like kind of like convoluted? Can you just dy and y?
Yeah, you can use dy, dx, and here we're using y primes now and y double primes. Whatever you like. All right, do you like that little substitution at the end? That's the trick. That's the one little trick I wanted to throw at you for taking the second derivative. Okay, so homework 2 will help you grapple with all of those ideas.
Okay, we have to get there quick. I got it. And Rebecca, there's games to do.
Okay, that's. Are we entitled to the table?
There's the function we just did. There it is. Did you want to look at this one? Look at these crazy curves. Bye, guys. There it is. That's the one we did earlier. Who knows? Woo. Bye, guys. Have a great day.
But technically, I was in both
Bye, guys.
because we're all